Now let's look at how you can define recursive functions over recursive data types in Haskell. Let's have another look at the data type that we saw in the previous part, namely the data type for binary trees. And suppose we want to define a function, let's call it SumTree, that computes the sum of the integer labels in our binary tree. And how can we define SumTree? Well, we define SumTree by means of pattern matching, and for each term constructor in our data type we're going to have a clause. So the first clause is the one for leaves. So for the term constructor bLeaf, if our tree is of the form bLeaf of n, then we expect the sum to be n. If we have a branching tree, that we have the term constructor bbranch and a label of the root n, and we have trees t1 and t2. Well, what do we do then? Well, here's probably a good idea to have a local definition to structure this a bit more. So let v1 be the result of calling SumTree recursively on the subtree t1, and v2 be the result of calling SumTree on the subtree t2. Then the result of calling SumTree is v1 plus v2 plus n. Let's give this to Haskell. Haskell was happy. Let's try to build a tree, our tree, and that would be a bbranch, and 7 would be the root, and the leaves would be labeled 8 and 9. Haskell is happy. Let's find SumTree of our tree, and my guess is that it's 24. Voila, it was 24 indeed. Now you may ask, what is the type of SumTree? Let's have a look at the code. Maybe we can figure it out. Let's see. So bLeaf is a term constructor that's applied to an int. So from the first clause of SumTree, we can see that if we call SumTree on a term that's bLeaf of n, we return n, then that tells us that the type returned by SumTree should be int. Now, what is the argument type of SumTree? Well, SumTree applies to any term of type btree, so an educated guess is that the type of SumTree should be btree to int. Let's see if that's the case. Let's find the type of SumTree by asking Haskell. Indeed, it was btree to int. So, isn't that nice? Well, in fact, we can do even more. Let's look at the following definition. What does it say? What we have here is a parameterized data type. It's parameterized with the type A. So what we've defined here is the type of A labeled binary trees, where A can be any type. So we can have integer labeled trees, we can have string labeled trees, we can have, well, many different kinds of trees. So what we have here, this thing, tree, is not a term constructor, a type constructor instead, because tree can be used to build types. Whereas leaf and branch are term constructors. So there is an important and not so subtle difference. Type constructors are used to build types. Term constructors are used to build terms of some given type. Anyway, so we can define parameterized, type parameterized data types. And with that in mind, we can then define functions over types. To do that, first let's have a look at some values that have type tree of A. Let's look at my tree. That could be a branch whose root was labeled horse, and then horse has two children. One could be a branch, rabbit, and a leaf, cow, and a leaf, parrot, and the other child could be a leaf, sheep. Here we go. Let's give this to Haskell. Haskell was happy. What's the type of my tree? My guess is it would be tree of string. Let's see what Haskell says. Yes, it is tree char list, and char list is the same as string. Now let's define a function that computes the number of nodes in a tree as just defined by our data type definition, and we'll see that this is yet another example of polymorphism. So the function I would like to define would be called number of nodes, and my guess is that if we give the function a tree of type tree of t, where t is any type, then we get back a number, a. So here we are requiring that a should be an element of the type class num, and if that's the case, we would get a function from tree of t to a. Now let's define number of nodes, and number of nodes is defined using pattern matching on the term constructors. So there are two term constructors in the data type tree. There's leaf and there's branch, so we expect to have two clauses in our definition of number of nodes. Number of nodes, when applied to the term leaf of n, should return 1 because there's one node. What if we call number of nodes on a branch n, t1, t2, where t1 and t2 are subtrees? Then first we should call number of nodes recursively, and we use local definitions to make that look a bit more modular. Let's say that v1 is the result of calling number of nodes on t1, and v2 is the result of calling number of nodes on t2, and oh, this should be t1, sorry. Then the result should be v1 plus v2, and there's the root as well, so that's v1 plus v2 plus 1. Let's see if Haskell likes that. Haskell was quite happy. Let's use number of nodes to find the number of nodes in my tree. There are 5 nodes. What if we use number of nodes on my other tree? What do we get? There are 3 nodes. No major surprise there, fortunately. What is the type then of number of nodes? Is it what we predicted? Let's see. Yes, it was what we predicted. Now, isn't that nice? For any type A in the type class num, then the function has type tree t to a. So this is a combination of ad hoc polymorphism in the form of type classes and parametric polymorphism because the function is defined for any type tree and tree of T.